All right, good morning, everyone. So everyone is present today. So just a reminder that as I present the lecture, feel free to post any questions as any doubts arise during the lecture. So what we will do today is continue our discussion about fundamental bioinorganic chemistry, but we're going to talk a little bit about some important inorganic chemistry bonding concepts that are key to understanding why metal ligand interactions occur. So this should be, to some extent, reviewed to some of you. Those who've taken inorganic chemistry, this will be a very strongly review lecture. All right, so let's briefly touch upon the points that were presented in our previous lecture. So we emphasized that fundamentally, a coordination compound is a Lewis acid and Lewis base adduct, where the metal or metal ion plays the role of the Lewis acid, which accepts electron pairs from the Lewis base, in this case, ligands serving as the Lewis base. We discussed the general ligand properties of denticity and hapticity, and this has to do with how these ligands interact with the metal center at how many points of contact and how many electron pairs are involved. Then we talked about the relationship between coordination number and geometry and emphasized that this relationship is strongly hinged on the idea of having ideal structures. We then further expanded on the Lewis acid and base theory to look at how hard soft acid base theory, which is again a subset of this theory, allows us to have insight into the preference of metal ligand bonding and the idea that hard acids prefer binding hard bases, soft acids prefer binding soft bases. And then we next looked at how this concept can help us to identify metal binding moieties or atoms within proteins and nucleic acids, and focusing on the different features of these polymers. So what I want to talk about now is going beyond just the idea of polarizability, which is fundamental to this hard soft acid base theory, but really thinking about orbitals and the orbitals that will allow for interactions between the metals and the ligands. And so to be able to do this, we have to have a sense of dimension. And so as I mentioned to you previously, a number of the compounds that you'll be looking at or that you'll be reading upon are structurally defined. And so they have a certain geometry, and that allows us to understand different properties. And so what we're going to look at here is to get a perspective of dimension. And so what I have here is a drawing of a coordinate system in which we will look at the placement of atoms, but also think about the placement of orbitals. All right, so here we're going to focus on orienting orbitals in terms of the directionality using a right-handed Cartesian coordinate system. So you often will hear me refer to this as the XYZ coordinate system, but just to give us a perspective of this. All right, so let's start with the s orbital, which we're all familiar with. This is a spherical orbital, so it's homogeneous throughout. And so the way that we can envision this in terms of positioning on this particular coordinate system is by placing it at the center of the system and just defining that spherical distribution. Then what we'll do is look at the p orbital. And so we know that there are three different types of p orbitals. And so something that you were presented since the beginning of your discussion of chemistry in terms of orbitals is the directionality, or at least the notation of the p orbitals in terms of either an x, y, or z node. And so what we're going to look at that is in terms of its positioning in this particular system. So here I present to you the drawings of the PZ, the PY, and the PX orbitals, and noting that the subscript refers to the positioning of those orbitals in this particular Cartesian system, where you have the PZ aligned with the z-axis, you have the PY, which is aligned along the y-axis, and then you have the PX, which is aligned along the x-axis. Now, again, I want to emphasize that you need to see this in a three-dimensional fashion so that x-axis is actually perpendicular to the plane of your screen, whereas the y-axis and the z-axis are found right on the plane of your screen. All right, so that z-axis is actually pointing out directly at you. Sorry, the x-axis is. All right, so then we're going to then explore the d orbitals. And so there are five d orbitals. And so we're going to look at their relative positioning with respect to the x, y, z. So here I present two of the d orbitals. And so these are the two different shapes that the d orbitals can adopt. The thing that we need to understand is that even though structurally or physically they look different, energetically, these d orbitals in a given element are identical in terms of their energy. And so the dz squared, as the z subscript denotes, this is affiliated with the z-axis. And so what we're seeing is the shape of two lobes, okay, that are aligned with the z-axis. And then you have this additional component here, this torsoid structure that is actually perpendicular to the direction of those two lobes, okay, and it's located right on the XY plane. All right, so that's actually going to be perpendicular to the plane of your screen. Then moving over to the dx squared minus y squared, this particular orbital is located, is positioned right on the x-axis. So you have these two identical lobes, and the y-axis, these two identical lobes. Now, something that I want to emphasize, and we saw with the p orbitals, and I didn't emphasize it there, is that you see that there's a different color shading. And so I'm not going to go into the specifics here. I'm going to actually clean this up. But basically, these particular shadings indicate that these are of different phases. All right, so this is the d orbital, and then when we look back at the p orbitals, you see the different shadings. Okay, and so that has a really important implication in terms of how these particular orbitals can interact with other orbitals. All right, so then going back to the d orbitals, so we looked at two of the d orbitals. So now we're going to look at the remaining three d orbitals, and as you can see, the remaining three look identical in shape to the dx squared minus y squared. And so one of the things I want to emphasize is that for clarity, what I did was I removed one of the axes in order to be able to show that these particular three orbitals are very similar in terms of their orientation. So what I've done here, for instance, for the dyz, was I simply remove the x-axis. Now, that is not to say that the x-axis does not exist there. It's just for simplicity, for us to be able to better appreciate these the orientation of these lobes. It's easier to remove the x-axis. All right, and so what you see is that these lobes are not aligned on a specific set of orbitals, yet they are positioned planar on the YZ plane. Then in a similar fashion, you have the DXZ. And so here I want to note that I basically have oriented us so that we have this in terms of the axes X and Z. All right, so I basically have repositioned the coordinates so that we can see this, but also I've eliminated the y-axis for clarity. And so again, we have a very similar feature where we have two lobes that are in phase, and then two other lobes that are out of phase with those corresponding lobes, and they are located on the XZ plane, and that is the reason why you have the subscript DXZ. And then finally, we have the DXY. So as that particular subscript implies, this particular orbital is oriented with respect to the X and the Y axis, but again, they're not directly on the axis. Rather, you have them in the plane of the XY plane. Okay, so you have a very similar shape. Again, even though four of these look identical in terms of their shapes, all five of these are identical in terms of energy when you're talking about an element. All right, so let's go back to this this correlation that we talked about with regards to coordination number and geometry. Because now what I want to do is look at how we can think about the orientation of these structures with respect to the XYZ system. All right, so we emphasize that when we have a coordination number one and we have a coordination number two, that we have a linear geometry. So what I'm going to show you is how you can basically place this in the XYZ system. just because of for simplicity, I'm not going to go into the details as to why. So the formal description of why you have certain orientation is something you would discuss in a fundamental inorganic chemistry course. I'm just going to show you, and if you want any further explanation, we can do so separately. All right, so with regards to the coordination number one, what we would do is we will place the metal at the origin, and then we'll have this oriented along the z-axis. So I have the ligand in the positive z direction, although I could have easily put that ligand in the minus z direction. But for simplicity, I have it oriented here. So that is located on the plane of your screen, right, and along the z-axis. In a similar fashion, we have the coordination number two, which is linear. And so we have the metal at the origin, and then we have the corresponding ligands position bounded to the metal along the z-axis, right? And so that's how you can see the 180 degrees. This is applied directly onto the z-axis. Then we look at the coordination number three, which applies a trigonal geometry. And so here, that particular structure is affiliated in this fashion, where you again have the metal at the origin, and what you're going to have is the rest of the structure on a plane, okay, because trigonal is actually a planar structure. This is going to be located on the XY plane. Okay, and again, there you can see your corresponding 120 degrees for your ligand metal ligand bond angles, characteristic of a trigonal geometry. Right, so we're going to move ahead towards the coordination number four. And again, we had two different types of geometries here. We had the classical tetrahedral geometry, which you guys are familiar with your corresponding ligand metal ligand 109.5 degrees angles. And so when we think about how do we position that on the XYZ, this one's a little bit tricky. So I have to use a little bit more perspective here to help you to see it. So what I've drawn here is a cube where I have the metal at the center of this cube, which is actually positioned at the origin of the XYZ coordinate system. And then at each of these particular corners, this one, this one, this one, and this one, is where you would find the positioning of those four ligands, okay? And so that's how we're able to maintain our ligand metal ligand 109.5 degree angles. And as you can see, none of these ligands are actually oriented with respect to a specific X, Y, or Z axis. All right, then looking at the square planar structure, okay, so this particular structure in coordination chemistry tends to be a little less common, okay? We'll talk a little bit more about the structure in later lectures. And so in terms of the XYZ coordinate system, that is a planar structure which actually is aligned directly on the XY plane. And as you can see, you have the metal at the origin, and then each of the ligands are on an actual axis. So you have these two ligands here positioned on the y-axis, and then you have these two ligands here that are positioned on the x-axis. And so that's how you're able to maintain your 90-degree angle. So you have here 90 degrees, and then you have here 90 degrees. So it's very important for you to keep in mind the angles that a particular structure denote and how you can position those angles so that it aligns with the XYZ coordinate system. It has to go hand in hand. All right, so we move on to coordination number 5. And then here we have structures that now have distinct positions for where the ligands are bound to the metal center. So if we focus on the trigonal bipyramidal structure, then we note that there's ligands positioned in what is known as the axial position, and then ligands positioned in the equatorial plane or the equatorial positions. All right, so focusing on this particular structure, and again, we have to think about this in a three-dimensional fashion, where we have the axial position, okay, that's going to give you a ligand metal ligand angle of 180 degrees. And then with respect to the equatorial plane, well, you have a trigonal structure. So then we have to account for the 120-degree angles, and also keeping in mind that that particular trigonal structure is going to be aligned perpendicular to the axial position. So they should be aligned perpendicular to the plane of our screens. So then how do we draw that on the XYZ coordinate system? Well, then we have the axial position that is aligned with the z-axis, and then that trigonal planar structure will be aligned on the xy plane. Right? So that's how you have your perpendicular orientation. In much a similar fashion, we have the square pyramidal structure, where we have a axial position and we have ligands in the equatorial plane. So as you can imagine, now that we're getting a sense of how to position these molecules, well, the axial position is placed along the z-axis, and then the ligands that are part of the equatorial plane, and especially accounting for those ligand-metal-ligand 90-degree bond angles, well, then we have them positioned in such a way that they are lying on the y and the x axes, all right, so that we can form that square pyramidal type of structure. All right. So the last one that we're going to orient is the coordination number 6, the octahedral one, which, as I mentioned previously, if we're talking about a octahedral compound in which the ligands are all identical, it turns out that none of these positions are actually different from one another. But formally, looking at it from this perspective, we will distinguish what is the axial position from what is the equatorial plane. All right, so as you can imagine, this is very similar to the coordination number 5 square pyramidal structure. And so in a much similar fashion, you're going to have the axial position aligned with the z-axis, and then you're going to have the equatorial plane positioned right on the xy plane. Okay, so there you get your perpendicular orientation of the equatorial plane with respect to the actual ligands. Okay. All right. Again, any questions, please post them in the chat, or you can get onto your microphone. All right. So I wanted to introduce that so that we can then start thinking about how we can consider the interaction of the metal orbitals with respect to ligands. Okay. So we're going to transition in a moment into a bonding theory that allows us to really explore this. But before we do so, I just want to remind us about some of the periodic nature of the periodic table. So we're just going to very briefly review the composition of the periodic table. So when we're talking about the elements with respect to the periodic table, so with regards to groups 1 and 2, and also 13 and 18, and I will show you in the periodic table where that's positioned. These are referred to as the main group elements. All right, so I'm going to go to the periodic table. So we're talking about group 1, group 2, okay, and then we're also talking about all of these over here, all of these groups, okay. Let's go back then to the previous slide. Then when we're referring to the elements that are in groups 3 through 12, well, these are called the transition elements, but they're also referred to as the D block elements, and we'll emphasize that in a moment. All right, so let's look at that in the periodic table. So we're talking about these particular groups, and those define your transition elements. And then finally, we have those set of elements that are located within the transition element series, which are known as the inner transition elements, commonly referred to as the lanthanides and the actinides. And another common phraseology is the F block elements. All right, so where are those located? Well, they're located here, okay, which are part of the transition element series. All right, so we have a perspective of where, when we refer to certain elements, where they're positioned in the periodic table. All right, so I'm emphasizing this because I want to start to think about this idea of filling in orbitals, all right? So we're then considering the application of electrons in these orbitals to then start to think about the energy of these particular electrons, because the energy is dictated by the orbitals in which they are positioned. All right, so this goes into what is known as Aufbau's principle, and that is essentially a building up of electrons to increasingly higher energy orbitals. In other words, you place electrons first into lower energy. Lower energy implies stable orbitals. And then as you fill up or occupy those orbitals, then you have to position the electrons into higher energy ones. The energy of orbitals is defined by specific quantum numbers, n, which is the primary quantum number. And generally, n gives us a perspective of the energy, and L, which is the angular momentum quantum number. Generally speaking, we actually consider the summation of the values of n and L, so n plus L, to indicate the relative energy. So the higher n plus L is, the higher the energy is. And so that is with respect to the energy of the orbitals. So you might wonder, if two orbitals have the same n plus L values, it turns out that the one with the lower value of n will be lower in energy. All right, let's look at examples. Okay, so here we have the examples where we have n plus L. Okay, that corresponds to these two orbitals, the 2p and the 2s. Okay, so we'll break these down. So if it's the 2p, okay, here we have the n equals to 2, and then we have L equals to 1. Okay, so then you have your n plus L, that will give you a value of 3. All right, so then if we have the 3s, well, then we have n equals to 3, and then we have L equals to 0, which will give you a value of n plus L of 3. All right, just to remind us where these numbers are coming from. All right, so as this indicates, then the 2p would be lower in energy than the 3s. All right, so thinking about that, and we're going to start applying Aufbau's principle, I want to also get us affiliated with where in the periodic tables are you going to find a certain set of orbitals. All right, so let's review that. So here in groups 1 and 2 is referred to as the S shell. So that's where you will find your S orbitals, and also not to forget helium, right, which is part of the 1s orbital. Then we have over here, all the way to the right of the periodic table, those the section of the periodic table that corresponds to the p shell. So that corresponds to your p orbitals. All right. So the reason why you have a total number of 6 groups that correspond to the p shell is that because in a particular row, you're going to have a total of 3 p orbitals. Okay, so reminding ourselves, we're talking about the px, the py, and the pz. Another really important thing to remember is that every orbital can be filled at maximum by 2 electrons. So if you have 3 p orbitals at maximum, they should be filled by 6 electrons. Okay, and that corresponds to these 6 groups you have there. Then you have the d shell. Okay, and so the d shell, as you recall, you have 5 d orbitals. And so here you have a total of 10 groups, because the maximum number of electrons that can fill in the 5d orbitals will be a total of 10. And then, not to forget that these 2 members down here, the lanthanum and actinum, these also are part of the D shell. But this also brings us to what is referred to formally as the F shell. And so the F shell, if you guys remember, there are 4 F orbitals. Okay, and so you should have a maximum number of 14 groups here to fill in the total of 2 electrons per orbital. All right, so that gives us a perspective of where the orbitals you would be applying electrons into. All right, so now we're going to formally apply Aufbau's principle. And so here we're looking at, and this is review, so this is not meant to really be a challenging thing. Just want to highlight a few things with regards to what is formerly known as the electron configuration. Electron configuration is very important because it helps us to identify what is the actual valence shell of a particular element. Because typically, when we're talking about bonding interactions, we're typically focusing on the valence orbitals because those are going to be the ones that are typically accessible for bonding. All right, so if we're focusing on a proton, okay, so that's the beginning of the periodic table. All right, in terms of the quantum numbers, and again, we're focusing on the valence shell here, but overall, we're building up to its electron configuration. So for the proton, the electron configuration would be 1s1. As you know, there's only one electron, and that's going to be located in the 1s orbital. So if we're trying to define this 1s1 electron, well, in terms of its quantum numbers, n, l, and then m sub l, which is the magnetic moment, well, we would have the quantum numbers 1 for n, 0 for l, and then 0 for m sub l. Now, if we're looking at the helium, okay, and so here you're going to have 1s2, okay, so 1s2 being the maximum. So first of all, the 1s orbital can be filled with a maximum of 2 electrons. So here you would have occupied the orbital itself. And then these are the corresponding quantum numbers to be able to define this particular arrangement of the electrons. All right, so moving ahead then, when we're focusing on lithium, so if we have, and actually let's go to the periodic table so we can see this, and I'm going to actually clear this out so we can see this better. So we've done hydrogen, we've done helium, we're here in the periodic table. So when we're defining the actual electron configuration, we already have, by the time we get to lithium, which is going to be located in the n equals to 2 shell, we would have filled in the 1s orbital, so 1s2. And so then here we would be 2s and 1 for the 1 electron that's going to be positioned there. All right, so keeping that in mind then, focusing on here, these would be the quantum numbers that would apply to the lithium element. All right, so I'm going to speed ahead because you guys should be very familiar with this. Looking at the example of oxygen, so let's go back to the periodic table over here. So I'm going to clean this up. We're focusing on oxygen, so we're here. All right, so then we're going to remind ourselves of the electron configuration. So the oxygen is positioned in the n equals 2, so we have n equals 1 here, n equals 2. Once we start getting here, we would have filled in the 1s2, okay? Then we would have filled in the 2s2, okay? And then we're here, which would be in the p block, or the p shell. And so that would be 2p, and based on its positioning here, that would be 2p4. Okay, so that would be the electron configuration for oxygen. And so what I have over here is the corresponding set of quantum numbers that would correspond to oxygen. And so here we have a few different options that are probable. And so the primary quantum number for the valence shell would be 2. Okay, this is corresponding to this orbital right here. Okay, and then here, because we're referring to the p orbital, we would have a value of L equals to 1. But then for the m sub L, we have 3 different options. Okay, and so you have a value of -1, 0, and 1. Okay, and that corresponds to the px, py, and pz orbitals. And so those are our way to be able to distinguish between the 3. Just to remind ourselves energetically, okay, focusing on the valence shell of this particular orbital, and we're focusing on the n equals to 2 shell, okay, that being the highest energy. Well, we have the 2s orbital, which will be lower in energy than the 2p. That will be full of the 2 set of electrons, okay, in opposite spin. Then we have the 4 remaining electrons, which will occupy the 2p orbitals. And so you have those 4 electrons, and that 4th electron, that one can be there, or it can be here, or it can be over here. And the reason for that is that energetically, they are all equal in energy. And so when orbitals are all equal in energy, there's a particular terminology that we use, and that is the terminology of degenerate. Okay, and degenerate implies equal in energy. All right. So up to here, this should be a review for everyone. But now what we're going to look at is how do we consider Aufbau's principle with respect to transition metals, okay, and then thinking about the electron configuration. And so here, a few things that are really important to point out is that when we are filling in the electrons into the orbitals, the n plus L value is going to be very important. Okay, and so really important to think about is the um, the energy of the d orbitals. Because whenever we're focusing on transition metals, okay, or the transition elements, the d orbitals are going to be very critical. So I have a special note here, and that is that we'll start to, as we enter into the transition element series, okay, and that's going to be in the n equals to 4 row. Well, one thing to keep in mind is that the 4s orbitals are actually going to be filled before the 3d orbitals, okay? But once they are actually filled, it turns out, and filled with electrons, it turns out that the 4s orbital will become higher in energy. Okay, so that part should be pretty obvious to us. Okay, based on just our understanding of the quantum numbers. But sometimes students do get confused in terms of this idea of putting in electrons into the 4s orbital first, but then taking out electrons. There is a little bit of confusion as to where. So what I'm going to do here is going to review how do we think about this. So I want to go back to the periodic table so that we can actually see it together. Let's clean this up a bit. Oh, sorry. All right. So once we're into the this region of the periodic table, and so we're here focusing on iron, we would have been n equals to 1, n equals to 2, n equals to 3, n equals to 4. Okay, so we're here. All right, so in terms of the Aufbau's principle, so the building up of electrons, lower energy orbitals to higher energy orbitals. So what we'll have, I'm going to write them down here. 1s2, okay, that corresponds to filling in those orbitals. 2s2, 2p6, okay, that corresponds to here. Then we have 3s2, 3p6 here. So now we are entering into this row of the periodic table, okay, so that we can figure out what is the electron configuration of iron. Well, here, what we hit first with are the S shell, okay. So as I mentioned already, you actually place electrons into the 4s orbital first, okay, and just by the design of the periodic table, that becomes obvious, okay. So then we'll put 4s2, okay, and then you have iron, which is positioned in the 1, 2, 3, 4, 5, 6, in the sixth position of that first transition series row. So that would be 3, D, and then a total of 6 electrons here. All right, so that would be formally the electron configuration with respect to iron. Let's go back over here. And so that's what we have defined here. But as you all know, we typically will represent electron configuration in abbreviated fashion. So what one does is we'll cap the electron configuration for the noble gas configuration that's closest to it. So in this case, it would be argon, which we put in parentheses, and then we'll have the remainder of the orbitals with the corresponding electrons, which in this case would be 4s2, 3d6, where we're emphasizing the valence orbitals. And what I mean again by valence orbitals, I mean the highest energy orbitals. All right, and so if we're focusing on the 3d orbitals here, well, here is a selection of the quantum numbers, where n refers to the primary quantum number for that particular orbital, which will be 3. L refers to the orbital itself, which is 2, because we're referring to the d orbitals. And then m sub L refers to the 5 different d orbitals and how we use this particular quantum number to be able to distinguish them. Right? So here in this particular context, we have 5 different ones ranging from -2 all the way up to +2. All right, so that's just to remind us about how we fill in terms of the, um, the quantum numbers themselves. All right, so now focusing on iron. Okay, so here, sorry. Once we have already filled in these particular orbitals with electrons, this would be the positioning in energy of the orbitals, where the 3d orbitals will actually be lower in energy than the 4s orbitals. And so here we have our 2 electrons in the 4s orbitals, and then we have our corresponding 6 electrons in the 3d orbitals. And then these 5 3d orbitals, well, they are all degenerate. Okay, so that's important. All equal in energy, so that one extra electron which is paired up can actually go into any one of these. Energetically would be the same. All right, now let's start to think about what happens if we undergo an oxidation or a removal of electrons from the metal center. So when focusing on the first row transition metal, and we're looking at the removal of electrons, well, it turns out that removing electrons comes from the 4s orbitals before the 3d. All right, so going back over here, cleaning this up. Let's just keep it here. Reminding ourselves the relative energy of these orbitals. Well, that should be now intuitive. If you're looking at the 4s orbital, which is higher in energy, right, than the 3d orbitals, well, it makes sense that if you're going to remove electrons, you should remove electrons first from the highest energy orbitals, which would be here. Okay, and so if we start to think about then the electron configuration with respect to the oxidation state, well, it will be as follows. So what I like to do to make it easier to think about this is to reposition the orbitals such that you have the argon noble glass configuration 3d6 4s2. So then when we consider the oxidation state of 1, so the removal of 1 electron, okay, what you're going to see is a removal of the electron from the s orbital. Okay, so you see that we have a loss of 1 electron, and so this would be argon 3d6 4s1. All right, I see a question. John Stevens says, I can't see. Can I see the last slide? What last slide would that be?
The last slide before that one.
Okay. Sorry, sometimes my thing gets a little crazy. Let me get out of this. Okay, so this one?
Yeah, this one.
It'll be this one.
All right.
Do you have a question?
No, let's to see, just make sure what I saw.
Okay. All right, so if you consider then the relative positioning of these orbitals, so we've already moved 1 electron, and so that 1 electron came from the 4s orbital. When we then have a second oxidation event, okay, so now we have iron 2, well, then we'll remove the second electron from the remaining electron in the 4s orbital. Okay, so we remove it from here, and so then now we're left with the 3d6. And then if you undergo another oxidation, you have iron 3, we remove now electrons from what remains. In this case, what remains are the d orbital electrons. So now you will have 3d5. Okay, so that's just to give us a reminder of how we think about the electron configuration with respect to oxidation of the first row transition metal series. So I'm emphasizing that this is true for the first row transition metal series. All right, so a few things that to emphasize are exceptions. And so here I'm gonna highlight a few exceptions and give you a general explanation as to why they even exist. So you have half-filled and filled levels that are especially stable. So if we were to think about the off-balance principle for, let's say, chromium, okay, we would get this as our electron configuration. Applying everything we just said, you would come up with this result where you have argon 4s2, 3d4, and then the relative positioning of the electrons in the corresponding orbitals would be something like this. But it turns out that that is actually not the correct electron configuration. The correct electron configuration is going to be as follows, will be actually this, where you have 4s1, 3d5. So what happens is one of the electrons that we would have positioned in the 4s orbital actually will go into the 3d orbital. And so the reason for this is because there is a stability associated with having all the electrons filling in these orbitals, okay, even though if it's half filled. And there's an additional reasoning, which is that there is an exchange energy stabilization. In this context, then, you have all the orbitals with electrons in the same spin, and it's actually very easy for them to switch from one orbit to another, as it would not involve any potential change in the spin direction of these electrons. So that's a very general description of that, but that is one of the fundamental explanations to why you have this added stability for having half-filled orbitals. Then something that's going to be similar as far as exceptions occurs for copper. So if we were to focus on the application of the Aufbaum principle, well, you would have come up with this particular electron configuration. But it turns out that that is actually incorrect. So the correct electron configuration for copper would be argon 4s1, 3d10. And the reason for that is that that one electron that would have been in the 4s orbital actually goes to fill in all of the 3d orbitals. And so what you get is this added stability of having all of the 3d orbitals filled, and is essentially giving us what is known as the d orbital noble gas configuration. And that's a very highly stable arrangement of the electrons in these orbitals. Okay, so these are important exceptions, again, corresponding to the first row transition series. All right, so I wanted to remind us about this so that we can now start to think about the energy of the orbitals and also, very importantly, the directionality. All right, so now I'm going to look at fundamental bonding interactions between metals and ligands. And so here we're going to take all this together. And the main bonding theory that I'm going to focus on in this course, I will once in a while refer to a few others, okay? But the main one, for the purpose of being able to understand the majority of material that you'll be reading, is crystal field theory. So I would say that this particular theory is an older theory, but it still allows us to understand a number of really important chemical properties and a lot of the spectroscopy of compounds. But it is a theory that is limited. Okay, so this particular theory has to do with an electric field. So that's where you get the crystal. Sorry, you get the field component of it. The crystal is just basically this idea of an arrangement of the ligand. So a geometric electric field that is induced by the ligands surrounding the metal center. So this is an electric field that is felt by the metal, and specifically the metal orbitals, the metal d orbitals. So in this particular context, what we're focusing on are the ligands, but not as individual ligands, but rather as the ligand electrons and how they create an electric field around the metal center, such that then we can rethink about the ligands as point charges. And so here is my representation of the ligands as point charges, or these electrons that are around the metal center. And we are not actually considering the identity of the ligands nor the corresponding orbitals from the ligands. And so this ends up being an electrostatic model where we focus on the electrostatics between these point charges and the electrons in the metal d orbitals. Right? So from this perspective, we're mostly focusing on the ionic component of this interaction, not necessarily the covalent interactions. Although keep in mind that this is the metal ligand interactions are feature both ionic and covalent uh, contributions. So here, the consideration, the model is one that's more ionic in based, but still we're focusing on this idea of the electrons from the ligands being contributed to the metal d orbitals. All right, so this is our model. Okay, so the ligands as point charges interacting with the metal center. And so the easiest way for us to consider this, at least the classical approach, is by focusing on an octahedral geometry. Okay, so as we already have discussed, here we're talking about a coordination number 6, right? So we have those 6 negative point charges or electrons pairs that are surrounding the metal center. And so now we need to mentally think about, well, where are those electron pairs positioned, right? Um, and so we have to think about then the orientation of the molecule with respect to the XYZ coordinate system. All right, so we're going to do a little bit of review of what we have just discussed. And so here I'm going to just draw it on the slide. I'm going to draw the XYZ coordinate system. Okay, so keep in mind a three-dimensional perspective where that x-axis is actually pointing out towards you with respect to the plane of your screen. All right, so our metal will be positioned here, okay? And then we're gonna have the electron pairs, okay? So we have this electron pair, these two set of electron pairs that are going to be on the axial position, right? Formerly the description of octahedral. And then we're going to have these other 4 here, 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 here. So that means we have 2 electron pairs along the z-axis, and then we have 2 electron pairs that are along the y-axis, and then we have 2 electron pairs that are along the x-axis. All right, so as I was mentioning to you, what we're going to look at is the impact in the energy of these electron pairs on the metal d orbitals. Okay, so if we're keeping that in mind, right, that perspective, well, let's think about the positioning of the metal d orbitals. All right, so here we're going to again review what I have just showed you previously are the orientation of the d orbitals. All right, so I'm going to draw them to get our perspective. So this would be a drawing of the dz squared. Okay, and then we're going to draw the other orbitals. So I'm going to draw the x squared minus y squared. Okay, so that's those 2 orbitals. Okay, now let's draw the other ones. That's the dyz. Okay, so I think it gets a little bit tricky here, but I'm going to try to draw it. Okay, and that would be the dxz, and then finally that would be the dx Y. All right. So why am I actually drawing this? Well, I want to emphasize where are the points of contact between these point charges and the d orbitals, because that's actually going to be really important when we're thinking about the impact of the electric field created by these point charges on the energy of the d orbitals. All right. So again, why is that important? Well, remember, this particular model is one that's built off of electrostatics. So we have to consider how the impact of electrons from the ligand interacting with electrons that may be available in the d orbitals, because electrons with electrons, these having negative charges, what there's going to be is an electrostatic repulsion. And so that electrostatic repulsion is going to cause for a change in the relative stability of the orbitals. All right, so these particular point charges, well, we can think about which of these orbitals do they come into direct contact, and which orbitals do they not have any direct contact. All right, so let's see, you guys, looking at these the drawings here, which orbitals have a direct contact with the point charges? So you can write your answers in the chat. I'll give you a couple of minutes to do so.
Can you repeat the question? I was drawing the orbitals.
Everyone else, you can put into the chat. So which of the direct contacts do the orbitals have with the point charges? All right, so I see Claudia as the first one to answer. So she says dz squared, and then the dx squared minus y squared. All right, so, and also Isa says the same thing. The only thing, Claudia, you wrote d twice, is actually dx squared minus y squared.
Thank
Okay.
you for the correction.
All right, so and those are correct. All right, so what you have is that if you think about the positioning of these, you would have actually, and one electron pair here, one would have been here, so they would be indirect contact. I'm just drawing them with respect, just drawing them a little bit far apart, but they would actually be in indirect contact. And also this ellipsoid that's here, well, those would be in direct contact with the point charges that are on the plane itself. So you have all components of this orbital in direct contact with all of the point charges. And then the dx squared minus y squared, well, you have each of those lobes having a direct contact with the point charges that are located in the equatorial plane. But the dyz, the dxz, and the dxy, none of these orbitals come into contact with those point charges. All right, so, well, what is the effect then? So here I'm just have a better drawing of these particular orbitals just for perspective. Well, what's going to be the ramification of this? Well, the ramification of this is that we're going to see how the energy of the d orbitals are going to actually change in the presence of this electric field of an octahedral geometry. One thing I want to emphasize is the following. For transition metals in row n of the periodic table, we consider the effect of the ligand interactions with the n minus 1 d orbitals. So if we are in n equals to 4, we're going to focus on the 5 3d orbitals. If we're in n equals to 5, we're going to focus on the 5 4d orbitals. Okay. All right, so this is the perspective then. When the metal is on its own in the absence of any of the ligands, okay, so any of those point charges, all 5 of those d orbitals will be equal in energy, okay? So they will be degenerate. But then, if you start to think about electron pairs surrounding the metal center, so let's imagine this possible structure where you have a spherical distribution of electron from ligands, so these negative point charges all over the metal. Well, because of that spherical distribution, equal homogeneous distribution, well, all 5 of these orbitals will still remain degenerate. The only thing is that their relative energy will increase, right, because of that electrostatic repulsion that can occur. All right, so that's what occurs. But then, if we start to think about, well, what if we have then these geometric arrangement of the point charges. As you know, coordination compounds are very fixed in terms of their structures. Well, then let's consider then the octahedral arrangement. I'm not sure why. Okay, there it goes. In this octahedral arrangement of the point charges. So again, to emphasize further, how you have the context between the dz squared and then the dx squared minus y squared. We already have established that. And then, okay, we already have established that those are the two orbitals with direct contact with the point charges. Well, what then occurs is that you have a splitting of the energy of the orbitals, where all five of these, and so when you have this drawing here, that actually means that you have all five of them equal in energy. That's what that basically means. All right. Initially, all five of those orbitals would be equal in energy, but then in the octahedral arrangement, you'll have the splitting. And the splitting is as follows, where the orbitals that have the direct contact with those point charges would become destabilized, right, because of that electrostatic repulsion. But then those orbitals that do not have a direct contact with those point charges, well, comparatively, they become stabilized. And so formally, the way we recognize the relative destabilization or stabilization is with respect to the original energy of the d orbitals. Okay, and so you have this line that I'm emphasizing here, which is known as the barycenter. So the barycenter is our perspective of how much the orbitals were either stabilized or destabilized. Another really important thing is the separation in the energy. How do we characterize that? So we have these three orbitals, dxy, dxz, and dyz, that are stabilized. And then with respect to the higher energy orbitals, which are destabilized, dz squared, dxy squared, well, this separation, we formally refer to it as delta octahedral. Okay, so the full, if we were to completely write it out, it would be delta octahedral. You'll commonly see it as that depiction, delta OCT. And then in earlier descriptions, which we're now going to emphasize, this is also referred to as 10DQ. Just you'll see that, but we're not going to really talk about that particular description. All right, so then this separation between the stabilized and the destabilized. Well, then how do we characterize the separation with respect to the barycenter? Well, what we do is that we focus on this amount of stabilization of those orbitals, dxy, dxz, dyz, and we apply this particular note of negative 0.4 delta octahedral to define the relative stabilization of those three orbitals. And the reason why it's negative is because you're actually decreasing in energy. Whereas those two orbitals that are going to be destabilized, well, with respect to the barycenter, we have an increase of 0.6 delta octahedral. Okay. There's another really important thing that I want to emphasize, and so that these orbitals are defined with these labels. The stabilized orbitals are defined as T2G, and the destabilized ones are defined as EG. I won't go into the details because it actually requires more description of what does that really mean. So again, that would be a formal inorganic chemistry course for you to understand where those labels are coming from. But the T2G refers to these three orbitals being stabilized, and the EG refers to these two that are destabilized in the octahedral field. Okay, so these labels are specific to an octahedral arrangement of these ligands. All right, so let's talk a bit about delta octahedral and what does it really tell us about metal ligand interactions, because that is where we want to really emphasize is how does this really give us a perspective of the affinity of the metal and the ligand, okay, and sort of this drawing for their interaction. All right, so the magnitude, okay, so how big that separation is determined by the strength of the crystal field. So you have these two terminologies, weak field and strong field, where weak field, as the name implies, is actually referring to the smaller separation. Strong field refers to a bigger separation. Just give me 1 second, guys. I have to plug in. So as you can expect, delta octahedral for a weak field will be smaller in magnitude than delta octahedral for a strong field. All right. Then you have the D5 electron configuration, which is going to be our point of reference here for us to be able to distinguish between what does it mean to be a smaller separation, what does it mean to be a bigger separation. All right, so here I'm going to give you our perspective. So a D5 electron configuration, in the absence of any ligands, well, you'll have all 5 of your d orbitals are going to be equal in energy. They're all going to be degenerate. So all 5 of those electrons will go and fill in those orbitals, so you have a half-filled set of orbitals. All right, so here you have 5 unpaired electrons. But then when we introduce an octahedral arrangement of point charges, right? So that we have this type of structure that gives us a separation in the energy of the d orbitals. Well, then you have what is the weak field, okay, a small separation versus a strong field, a big separation. And here I give you an example of compounds that fall into this category, where one example for a weak field with a D5 electron configuration is iron with 6 aqua ligands, and the iron is iron 3 plus. Okay, so here iron will be iron 3 plus. And an example of a metal compound with a strong field would be iron 3 plus. But in this case, it is surrounded by 6 ligands that are the cyano-ligands. All right, we'll look at that in a moment. But so we have a weak field and a strong field. And what happens? Well, in the weak field, what happens is that the electrons will prefer to fill in the orbitals, whether there are the stabilized and the destabilized ones. And the reason for that is because there's less energetic penalty in filling in the higher energy ones than if you start to pair up, right? So the electrostatic repulsion of pairing up is greater than if you were just to have the electrons all completely separate. But in contrast, when you look at the strong field, the separation is so grand that the positioning of electrons in the higher energy orbitals will be too much that the electrons would prefer to pair up. As you can see here, they prefer to pair up than be positioned in the higher energy orbitals. All right, and so that gives us then a perspective of what does the magnitude of delta octahedral implicate, right? How does it affect? And what you end up seeing is that it can affect the number of unpaired electrons that we can have. Where in the case of the weak field, we end up here with 5 unpaired electrons. And then in the strong field, we only have 1 unpaired electron. Right, so you have unpaired, whereas in the strong field, you have this 1 unpaired electron. All right, so it's very important to be able to recognize then the implications of the magnitude. All right. So let's go back then and let's really think about, well, okay, why are we emphasizing so much about this separation in energy of the d orbitals? And what does it really mean about the formation of the metal ligand complex, right? And so one of the things that I want to do is to quantify the relative energy that a particular d orbital electron experiences in a coordination compound. So again, this separation corresponds to an octahedral arrangement. So let's keep that in mind. And what I'm going to focus on is a particular compound. So here I'm focusing on a titanium compound, titanium 3 plus. And we're going to look at what happens to the electron that's located in that particular metal ion. So we're focusing on a D1 electron configuration. So here, in the absence of ligand, you would have your electron at this energy level. Okay. But then in the octahedral arrangement, what you see is that electron now becomes positioned according to Aufbau's principle in the lower energy orbital. So it can be positioned there in one of the T2G orbitals. And so what essentially is happening is that because of that octahedral arrangement of ligands, was happening to the metal d orbital electron is that it is actually becoming stabilized. And so that gives us then a perspective of a thermodynamic drive. And a thermodynamic drive being that the metal d orbital electrons become stabilized in this coordination environment. And so that is a drive for why this metal would want to even interact with those ligands. But now let's try to get a relative quantification of this stabilization. All right, so if we were to try to denote this in terms of a d electron configuration, what you would say is that this is a T2G1 because you filled in one electron in those T2G orbitals. All right, so let's then try to quantify this idea of how stabilized the electron becomes. So we have this equation here that calculates what is known as the crystal field stabilization energy. Again, this particular measure is of how stabilized the electrons from the metal d orbitals become in the coordination environment. According to this equation, it is defined by the number of electrons in the T2G orbitals times 0.4 delta octahedral, that whole product multiplied by -1. Okay, so we're getting a measure of how stabilized those electrons that are in the T2G become. And then you add this to the number of electrons that are positioned in the EG orbitals up here times the factor 0.6 delta octahedral. So this whole summation gives you the value of the crystal field stabilization energy. So as you can see, if we were to apply this for a D1 electron configuration, well, we only have one electron, which is positioned in the T2G, so we'll put that one here, okay? We have no electrons in EG, right, so this is 0. So then you plug the 0 here, you get a product of 0. So if you were to then do the math, okay, you do the math, your value is a crystal field stabilization energy of 0.4 delta octahedral. So that means that one single electron became stabilized by a factor of 0.4 delta octahedral, or negative 0.4 delta octahedral, with respect to the Barry center. So again, the overall big picture, what is this really telling us? Is that a thermodynamic driving force for the formation of octahedral metal ligand compound can be the stabilization of the metal d orbital electrons. All right. So now we're starting to build up our understanding. We know hard, soft, acid, base theory can help us to understand the preference for binding, but this at the level of the orbital energies and the electrons positioned within the metal d orbitals, it allows us to understand why a metal will interact with the ligand in terms of stabilization of its corresponding electron. All right, so what are those factors that determine delta? Well, one of them is going to be the oxidation state of the metal ion, where the higher this oxidation state or the ionic charge is, the higher the magnitude of delta. Another really important one is the nature of the metal. Whereas you go down the rows of the transition metals, so let's say you're in transition metal with 4D and 5D, well, your magnitude will be really big. So typically, you're going to have what are known as low spin metal complexes, and we'll establish what low spin versus high spin even means. Another really important one is the number and geometry of the ligands. So as you can notice, I've mentioned delta as a general delta, not as delta octahedral, because delta refers to the splitting of d orbitals in any coordination environment, so in any electric field defined by the arrangement of the ligands, such that delta tetrahedral, as an example, tetrahedral is a coordination number 4, well, that delta is approximately 50% of delta octahedral on average, right? So that shows you that magnitude is quite small with respect to delta octahedral. But it also emphasizes how geometry has an impact on the actual magnitude of delta. And another really important one, which we won't emphasize too much, is the nature of the ligands. Because remember, if we're focusing on crystal field theory, we don't really take the identity of the ligands into account. But the reality is that model is incorrect. The identity of the ligands is very important. And so what we have here is what is known as a spectrochemical series. So here is just a partial series, an arrangement of ligands from left to right. And when we're going from left to right, what we are looking at, or what we're depicting, are those ligands that can induce a weak field. And as you go to the right, those ligands that can induce a strong field. So ligands can contribute to the magnitude of delta. So this particular crystal field theory, we would never be able to understand this series. So we would need a much more modern theory to really understand the premise behind here. All right, so for the last part of today, what I want to emphasize is how the magnitude of delta can then dictate the magnetic properties of the metal ion. And so I've already emphasized a bit with using the example of the D5 electron configuration, that if you have a weak field or a strong field, you're going to have a different number of unpaired electrons, okay? Well, you can imagine then how then the magnitude of delta can really have an impact on whether there's any unpaired electrons at all. All right, so when we're talking about the magnetic properties of a metal ion, we're talking about how the metal ion is going to respond, its electron is going to respond to the presence of an external magnetic field, where a paramagnetic compound that implies that it is a compound that has unpaired electrons, or at least one unpaired electron, will be attracted into the field. All right, so how do we see this manifested? Well, we see this in this plot here, where A is referring to paramagnetic species. And so what we're seeing is that that paramagnetic species, in terms of the external magnetic field, well, its magnetization actually increases linearly. So we see a linear increase of the magnetization as you apply the external magnetic field. Okay, so the strength of the externally applied magnetic field. And this is something that is at constant temperature. In contrast, a diamagnetic compound, so that is something that does not have any unpaired electrons, well, that's represented by the B in this diagram. Well, this will behave in an opposite manner, where the compound will be slightly repelled and decrease linearly with the strength of the external magnetic field. All right, so we see that opposite trend. All right, so then, to determine the magnetic property of a metal, and we're being very simplistic here, we need to define the electronic spin situation. And so how do we define that? Well, we determine that based on the number of unpaired electrons in the system, where the spin state, S, okay, that is equal to the summation of the spin moments for all the electrons in the atom or ion. Right? So MS can be, as you guys are aware, MS can be a value of plus 1/2 or minus 1/2. Let me just write that here. All right, so then looking at the spin state as a be able to dictate something as paramagnetic or diamagnetic. If you have a spin state of 0, that means that you either have no electrons or no unpaired electrons. So that's a diamagnetic situation. If you have a spin that is not equal to 0, so that means you have at least one unpaired electron or more, that would be something that is paramagnetic. So whether a d metal ion with d orbital electrons is diamagnetic or paramagnetic will depend on its coordination environment. Okay, so here, the electron spin is indirectly measured by determining the magnetic moment. So that's a particular property that's measured of a compound. So here what I'm showing you is a correlation between the property magnetic moment and the spin number. So this is a correlation in which is a simplified equation. This doesn't consider all the factors that can be involved, where mu is the magnetic moment and its correlation with the spin, or another way that we can look at it is with respect to the number of unpaired electrons. It's either or. And so here then, what one does is measure the magnetic moment of a compound in an external magnetic field. And based on then that magnetic moment, they can then determine the number of the spin state and consequently the number of unpaired electrons. All right, so it goes hand in hand. All right, so let's look at this in a particular example. So here we're focusing on chromium 2+, which is a D4 electron configuration. Here is a weak field representation, right? So small delta octahedral versus a strong field. Okay, so that's a bigger delta octahedral. All right, so what do we see then? In the weak field case, we have 4 unpaired electrons, whereas in the strong field, we have 2 unpaired electrons. So in the case of the weak field, we end up having then an S equals to a value of 2, because we have a total of 4 unpaired electrons, each one with a value of 1/2. So we have an S equals to 2. Whereas in the low spin, in the strong field, we have a value of S equals to 1. So now, if you look at the numbers, here is where we then formally define one situation as being a high spin representation versus the other situation being the low spin representation. Okay, so this is for each electron configuration, it's a relative terminology. Whereas for D4, S equals to 2 is its high spin version, and then S equals to 1, it's its low spin version. And that has to do with the whether it's a weak field, high spin, strong field, low spin. Okay, so I'm just emphasizing that, again, is relative to the electron configuration and obviously the magnitude of delta. All right, so if then we correlate this to the magnetic moment, right? We already have the spin value, then we can determine the magnetic moment. Well, then the magnetic moment for D4 weak field is a mu of 4.9, whereas for the strong field low spin, the mu is 2.83. All right, so if we were to independently have measured that number, we would be able to back calculate and determine what is the spin and the corresponding number of unpaired electrons. Another thing that we can do, just for emphasis of the idea of the crystal field stabilization energy, well, we can calculate that for both situations. For the D4 in the weak field, we have 3 electrons in the T2G orbitals and 1 electron in the EG. If we apply the math, we will get a value of delta of negative 0.6 delta octahedral. So that tells us how stabilized those electrons are. If we look at then for the strong field, low spin, well, we have 4 electrons in the T2G. We do the math, what we get is a number that is negative 1.6 delta octahedral. But we have to take in consideration that in this representation, there is a penalty due to a pairing. Because of that penalty, what we're going to apply to this is a factor of 1p. Again, we're using general terms here. 1p referring to that penalty because of the electrostatic repulsion from pairing up. But nonetheless, looking at these numbers, okay, both of these arrangements result in a stabilization of the metal d orbitals of chromium 2+. All right, everyone, I want to leave us here. And so we're going to continue. We're going to finish our discussion of this fundamental metal ligand interactions. All right, I'll see you guys on Thursday. Take care.
Professor, the last part I was a bit confused.
What's your question?
How can you get confused the part where you calculated the T2G the red letters that you put there? I got a bit confused there. How you got it?
There are 3 electrons here. So there's 3 in the T2G and there's 1 here. There's 1 in the EG. Over here, there are 4. So there are 4 in the T2G, and in the EG, there is 0. You see that?
Yeah.
Okay. And then we'll apply it into the equation, the crystal field's stabilization energy. So when we apply it there, the equation is the number of electrons in T2G, number of electrons in EG. Okay, so there are 3, and here there's 1. And then over here, there are 4 in T2G, okay? And then there are 0, right? So there'd be plus 0 because there's 0 EGs. So that's where we get those numbers in. And you do the math there, and then you end up with a value of 0.6 delta octahedral there, and over here you end up with a negative 0.6 delta octahedral, and on the right you end up with a negative 1.6 delta octahedral. So we're just applying that equation that I presented earlier. Do you see that?
Yeah, yeah, I understand it.
And again, that has to do with the separation of your delta octahedral, how big that separation is, whether they will not pair up initially or whether they start pairing up before they go into the higher energy orbitals. All right, then. If you have any other questions, just let me know. But we're going to continue on from here in our next lecture.
Okay, thank you.
All right, you're welcome.